No.
Hello, teacher.
Hello.
Yeah.
So we are still waiting for 2 more person. Maybe
Yeah.
I don't. Maybe we can start by an exercise just to make what we discussed yesterday a little bit more concrete, if that's all right with you. Hello, Billy.
Hello, teacher.
So let me first share my screen. Okay. Okay. So as you see, this is the end of what we discussed yesterday. And I just want to make a small break with an exercise. Okay. I have basically it's part of last year's exam. So this makes it even more concrete. This is the exercise. Okay. So I want to leave you a few minutes to really understand what it's about. Some of the questions are maybe difficult, so I would like you to focus on question 2. Okay. Compute the network predictions y hat 1 and y hat 2 on the training set. Okay. So right now, please take the time just to read the exercise. Can you see it well? Is it okay? Maybe I
Quite
can zoom in.
You can zoom in. Yes.
Yes.
Better.
Better?
Yeah. Okay. Good.
Okay, great. So I leave you a few minutes, 5 minutes to you can basically read it and start computing. Okay. So you see that you have basically values for the weights, for the biases, etc. You have different inputs, x1, x2, and so the idea is what is the network prediction for this input. Okay. Please don't hesitate if you have questions. I'm right here. Hello. So do you manage to start? Do you understand what you need to do? Maybe I can at least say a few words to help you. So first thing, so this is a neural network. First question, how many parameters does this neural network have? What's the depth of this neural network? Maybe? Anyone?
To depth.
Yeah, exactly. Depth equal to we have layer 1 here and layer 2, which is the output layer here. Okay, perfect. So then, number of parameters of the network. Remember, yesterday when we did it, you have the number of weights. Sorry. The number of weights and the number of biases. So what's the number of weights here?
9.
Yeah, exactly, 9. It's 9 because it's the number of basically W here. You have 2 times 3, 6, plus 3 times 1, 3.
Yeah.
And what's the number of biases?
4.
Yeah, 4 exactly. We have 3 plus 1. There is 1 bias per neuron. Perfect. So the thing is, when we will be training neural network, this will be later of this class today, we will see how we can find optimal values for these parameters. This is the goal of the training process. But right now in this exercise, we just assume that we have some parameters value. So they are given here. W11 equals 1. W12 equals 1. Here. W13 equals 0. W21 equals 0. W22 equals minus 2. And W23 equals 1. Okay, these are the first weights. Then we have B1 equal minus 1, B2 equals 0, B3 equals 1. Okay. And finally, B4 equals 0, W1 equals 1, W2 equals 2, W3 equals 0.5. Okay. Now, we will take two inputs, x1, which is 0, 1, and x2 equals 1, 0. So x1 equals 0, 1. The question is, if you input 0, 1 into this network, what is y hat 1? Okay. And same question with 1, 0 for x2. So there is one last thing I didn't say, I didn't comment on, it's this, leaky ReLU. So yesterday, I remember I will have introduced to you many activation functions, okay, including one that is called ReLU, okay, that looks like this. And leaky ReLU is a variant of that, which I will draw right now. Leaky ReLU. Okay, the equation is there. So from R to R basically, and to each x it associates alpha x if x inferior to 0 and x otherwise. Okay, and so with alpha equals 0.1. So this means what? This means that we have a leaky ReLU that looks like this. We have the positive side, which is like this, and we have the negative side that is like this. Oh, not very nice. Okay, leaky ReLU. Okay, so this means that here on these 3 neurons, we have a leaky ReLU activation function. And on the input layer, as you have seen here, it has a linear activation. Linear activation, remember, it means that it's completely the identity function, this function. Okay. So now, knowing all of that, can you try to compute me y hat 1 and y hat 2? Okay. I leave you a few minutes, maybe 5 minutes. So have you found any result?
I have a question. According to your formula, we need to compute the output or y. It's the function. It's a function with the parameter the weight, the weight and value of multiply the sum of for each weight multiply it x and plus with bias.
Yes.
But
So yes.
I'm not sure about the function. The function in this case it mean you ReLU.
So yes, in this case, for H1, H2, and H3, the function is leaky ReLU, and for this one, for y hat, it will be linear. Okay, so here, this is the f from here, and the leaky ReLU is the f for these ones. Okay.
Okay.
So maybe what we can do is start by drawing some kind of table. Okay, sorry. So we'll do a table. The goal is to compute y hat, but initially we first have to compute h1, h2, and h3. Okay.
Yeah.
So let's do a table. We'll get our x. Oh, sorry, bad color. We have our x1 and x2. Okay, x1, for example, if we use the first input value, okay, let me start again. We will draw a table. We want x1, x2, then h1, h2, h3, and then y hat. And we'll do that with x1 and x2. Okay, so maybe I can draw something like this to make it more clear.
Yeah.
So what are x1 and x2? When we look at x, the first data x1, the first data x1 is 0, 1, so it's like this. Okay. If we want h1, okay, h1, maybe I should write it there. I will erase that. Let's write the equation. h1 equals leaky ReLU of W11 multiplied by x1
Yes.
plus W12 multiplied, no, sorry, W21 multiplied by x2.
Yeah. Plus B1.
Plus B1, exactly. Okay, so let's use the numerical values. W11 equals 1 multiplied by x1, 0. So this is 0. Plus W21, which is 0 multiplied by x2, so it's 0. And B1 is minus 1. So this is minus 1. And when we apply leaky ReLU to minus 1, okay, we are on this part of the formula, we get alpha multiplied by minus 1, and alpha equals 0.1. So we get minus 0.1. Okay?
Yeah.
Is that, did I go too fast, or is that okay for everybody?
I think it's okay.
Okay. Okay, so now if you have seen the ID, you can compute H2 and H3. Same for 0, 1. And one is you had, maybe I just unzoom a little bit. Oh, zoom out. Okay. And once you have H2 and H3, you can compute y hat using these values, this bias, this value of H1, H2, and H3, and you will have y hat. Okay? I will do it at the same time. Okay, so these are my computations. Maybe I'll just explain it very quickly.
Yeah. So
and then later, yes?
why has it been the leaky from H1 multiply with W1?
Yeah, exactly. It's y hat equals linear of h1 multiplied by w1 plus h2 w2 plus h3 w3 plus b4.
Yeah.
And linear, remember, linear is exactly the identity. So linear means x gets x. So in fact, we don't need this. It's exactly this value. Okay. So here I got h1 equal minus 0.1. If we try to compute h2, it is 1 multiplied by 0, so 0, plus minus 2 multiplied by 1. So it's minus 2 plus b2, still minus 2. And remember, it's leaky value. So minus 2 leaky value, it's minus 2 multiplied by alpha, so minus 0.2.
Yeah.
And then for h3 is 0 times 0 plus 1 times 1, so it's 1. Plus 1 is 2. And for leaky value, if you have 2, it's the identity, so you get exactly 2. So these are h1, h2, and h3. And finally, to get the y hat, you just need to multiply minus 0.1 times 1 plus minus 0.2 times 2. Okay, so this makes minus 0.1 plus minus 0.4 plus 2 multiplied by 0.5. So the whole thing makes 0.5 plus 0. So the total is 0.5. Maybe I can write it. 0.5 equals 1 multiplied by 0 minus 0.2 minus 0.1 plus 2 multiplied by minus 0.2 plus 2 multiplied by 0.5 plus 0. If you compute this, it's exactly 0.5. Okay, so this is the answer for the first input, and the second input, you can verify it yourself. It must be 2.5. I leave you sometimes. Sorry, I have a comment. I think h1 for x1 is 0. It's long, right? You say this should be 0? Okay, let's compute again. Maybe I made a mistake. So h1 should be equal to this multiplied by this. So 0 multiplied by 1. W21 equals 0. You would be right, but I think, yes, this 0 is... okay, no. Oh, what did I write? In fact, yes, this 0 is for W21 and this W13 is 0 as well. Yes, so this is for here, in fact. Maybe I can... Is it okay? Is it clearer?
Yes.
Okay. So it's minus 0.1, I think. No problem. No, you say 1.2. W11 equals 1. Okay. And W21 equals 0. So it must be 1 times 0 plus 0 times 1. So it's 0. Minus 1 is minus 1. And then when you go through leaky value, minus 1, you get minus 1 multiplied by alpha. And alpha is 0.1. So it's minus 0.1. No, I think it's correct. Please tell me if you don't see why it's minus 0.1. No, it's all right? Okay. So today, now I wanted to do this exercise, but also because it's the beginning, and so it gets us everybody on the same page, but also because I wanted to make it a little bit more concrete than yesterday. Yesterday it was only math and explanations, and okay, today you see what is really a neural network, how you compute output from the input, how you use the parameters. Okay, and in this exercise, the parameters, as I was saying, are given to you, but in the real life you have to learn the parameters. Okay. I don't comment for now the rest of the questions because this will make sense a little bit later. I want to comment one thing though. You see that in this network, I have a different activation function for the hidden layers and for the output layer. And this is important because in fact, you always, not always, but it's always the case that you will choose independently the hidden layer activation function and the output layer activation function. Why is that? It's because the output layer activation function depends on the problem you want to solve. Okay, you will choose the activation function of the output layer according to the type of problem you want to solve. And here, you see, I was asking last year because last year I spoke a little bit about regression. This year I don't speak much about it. So this year I would not ask you such a question at the exam, but still, the question is: do you think this neural network models a classification or a regression problem? So, in fact, the answer will be given to you by looking at this y-hat. You see, y-hat allows you to predict 0.5, 2.5. So it looks a little bit like the continuous values for this y-hat, for this output. And remember, yesterday, when I spoke about, let me get the PDF of the first class, when I spoke about machine learning, supervised machine learning, I told you there are two types of problems. A type where you have continuous output and a type where you have discrete output. And continuous output is called regression. discrete output is called classification. So in this case, you see that basically, since the output looks continuous, it would be more a regression problem. Okay. I don't say much about the cost function because I will say more today. Let me continue. If that's all right, I will continue on the class. Okay, because precisely my point now is that I want to speak to you about how do you choose the output layer activation. Okay, that's all right with everybody. Do you have question? I think there's a question. Yes, go on. Please. No question?
Not yet?
Yes. Okay. Okay. No question. Okay. So I go on. So as I was saying, I now speak about output layer, and I say suppose we have defined a neural network such that the last layer equation is y equals f of h. So h is the hidden layer, the last hidden layer. Okay. And basically we have y, the output, that depends on h with a certain function f. Okay, so now how do we choose f to perform classification? So f, I mean the activation function of the output layer. Okay, whenever we speak about classification, usually we will typically distinguish two cases. There will be a first case where we will speak about binary classification. So, in case we want to choose between two possible classes, we can always rewrite the problem such that y equals 0 or 1. So when you have a binary classification problem, remember we gave an example of binary classification yesterday. We said, for example, a comment on YouTube is spam or not spam. Okay, so usually if you want to classify spam, not spam, you will consider that not spam is 0 and spam is 1. Okay, same thing. I mentioned yesterday a case. For example, if you want to look for a tumor in medical imaging, if you look for it, if you find the tumor, it will be 1, and if you don't find the tumor, it's 0. Okay, so it's very usual to rewrite, to reformulate a problem, a binary classification problem under this form 0, 1. And in this case, if you have this 0, 1, it is a very good idea to use a sigmoid function for the activation layer. Good idea to use a sigmoid function. For F. Okay, remember the sigmoid? Yesterday we defined it. Let me try something. Would be very nice if I could just select this. Oh, magnificent. I don't need to rewrite it. Okay. This way I'm going quicker. Okay, so this is the sigmoid. This is the sorry. This is the, maybe I will rewrite that properly. The equation of the sigmoid. Okay. 1 divided by 1 plus exponential minus 6. And this is the general shape of the sigmoid. And you see something very interesting. Basically, if you look at the values of the sigmoid function, the values is not 0 or 1. It's all the values between 0 and 1. So this means you can predict 0 or you can predict 1. But in fact, you can also predict all the intermediate values. And if you can predict all the values between 0 and 1, in fact, what you get is very similar to a probability. Okay, so the sigmoid value, the sigmoid function, provides a value that is homogeneous. Homogeneous meaning is very similar to a probability. In which probability, which we could write P of y equals 1, knowing x. Okay, so given a certain x as an input of our neural network, if we use a sigmoid function at the output of our neural network, what we get will be something between 0 and 1. And if it gives a value that is close to 1, it means that the probability of saying, okay, this x is spam, for example, this probability will be very high. And if the probability is very, very high, superior to 1/2, for example, we can say that, okay, this is spam. If it's inferior to 1/2, we would say, no, it's not spam. So in fact, what we really do when we use a sigmoid is then when we really want to classify 0 or 1, we split there. Oh, sorry. We split here. Here is predict 1, and here is predict 0. Okay, I lost this. This is how we really use it for binary classification, but the information that we get from the sigmoid function is much richer than only 0 or 1. It tells you also the confidence of the algorithm. If you get something like this, so you get a value here for y that is maybe 0.6. 0.6 means, okay, it's probably 1. Okay, it's probably spam, for example. But 0.6 also means that you don't have a lot of confidence in predicting that this is spam. If you had, for example, here 0.99, then you would be much more confident in saying, okay, this comment is most likely it's spam. But with 0.6, you're not sure. Okay, so this probability value gives you also more information because it gives you some confidence on whether you are certain or not to predict 0 or 1. Okay. Do you have questions about that? The only thing that is important in everything I said is that if you are doing binary classification, you should use a sigmoid function as an output. Okay, that's all. If you only remember that I'm good with that. That's the most important thing. Okay. This is all for binary classification. And if now we look at multi-class classification, because basically we have two cases. Either we have only two classes, either we have many classes. And in this case, we are not interested in predicting P of y equals 1. We are interested in predicting P of y equals I, knowing x. And I is what? I is a class index, okay, from 1 to n. N is the number of classes. Okay. So to do this, we use something that is called the softmax function. Softmax is kind of a generalization of the sigmoid function, but if you have a higher number than only two classes. So let me give you the formula of the softmax function. To do this, we use the softmax function. And we have softmax of z I equals exponential of zi divided by the sum of exponential of, say, g for g equals 1 to n. Okay, and this is yi. What is z in this formula? Let me draw a neural network. You have maybe something like this. Okay, then you have a second. Okay, and then here, this is your output layer. So this is maybe you have 3 inputs, let's say x1, x2, x3. This is your layer 1, this is your layer 2, and this is your output layer. What I call Z in my previous slide, Z here, Z would be what you get here. Z1, Z2, and Z3. And Z, for example, here would be this multiplied by this, plus this multiplied by this, plus the bias. Okay. And later, in order to get y1, sorry, y2, y3, then you will apply the softmax to all of this in order to get y1, y2, y3. Okay. So if I come back to my previous to this slide here, in fact, maybe I can take the orange. When you define the value of a neuron y, f is the activation function, okay? You have f of this. This, we often refer to it as z, okay? Z is the combination, the linear combination of this multiplied by this, plus this multiplied by this, etc., plus the bias. This is z, okay? So now I get y1, y2, y3 doing such combination of Z1, Z2, Z3. Intuitively, what happens when you do the softmax? Okay, suppose you have this. Suppose, example. Oh, sorry. If we have Z1 equals 2, Z2 equals 0.2, and Z3 equals 1. Okay. If you compute Y1, Y2, and Y3 using the softmax, so if Y1 equals softmax of Z1, it will give you, I have to make the computation, I'm sorry, I don't have it. Let me open some MATLAB to do the computation. I'm doing it live. So Z equals 2, 0.2, and 1. And I will Y equals exponential of minus Z divided by the sum of exponential minus Z. This is so weird. Ah, yes. Excuse me. Okay, this is 0.65. Zero point 11 and 0.24. Okay, so what does it mean? You see that one very important property is that the sum of y1 plus y2 plus y3 equals to what? Can you compute it? Can you tell me?
Zero dot 1.
Yeah, thank you, Billy. Okay, 1. Very important. Why is it important? Because this, it's sum to 1. It's a property of this. Of course, if you look at the formula, if you sum yi plus y1 plus y2 plus y3, you will get exponential of z1 divided by the sum of exponential of all the z, plus exponential of z2 divided by this sum, plus exponential of z3 divided by this sum. So in fact, you will have the sum of all the exponential divided by the sum of exponential, so it gives you 1. And that's a very good property, because basically it means that this can be seen as a distribution, a probability distribution. Okay. And the probability tells you that you have a large probability to get classified as the first class, a quite low probability of being classified as the third class, and a very low probability to be classified as the second class. Okay, and this all comes from these original values where you can see that 2 was predicted, then 1 here, and then 0.2 here. But basically, softmax helps you to reformulate these values into probabilities. Why probabilities? Because as I said yesterday, whenever we do machine learning, in fact, what we really do is statistical learning. And statistical learning always acts better if you use probabilities. Okay, that's not a very satisfying answer, but that's the real answer anyway. Okay, so I just want to write that using a softmax. Provides a probability distribution over all classes, which is exactly P. P of y equals 1 according to x, P of y equals 2 according to x, P of y equals 3 according to x. Okay, so whether it's binary classification or multi-class classification, we use sigmoid or softmax function, and the goal is to get something that is similar to probabilities. And in fact, you can also notice that softmax, if you have only two classes, softmax becomes equivalent to this. Okay, to sigmoid. Okay, I'm done with that. And now I would like to speak to you about how to train your network. But first, I would like to take questions if you have some. If you have no question, I want to save this PDF. Okay. I'll send it to you by email right now, like always.
Yes.
Yeah. Thank you.
Okay. The PDF. And I will start a new one. Which I will call class 3. Okay, it's class 3, but it's the second class. You understand, it's just a separation of the content. It's not the class 3, okay? So class 3 will be about how to train neural network. Okay, this one might get a little bit theoretical. I won't finish today, I think, but it's okay because I only need to speak until binary classification, I think. Yeah, I will give you the binary, and that will be all. Okay, let's go. Later today, I hope we can start doing a lab because this is a lot of theory until now, and at some point, I'm sure you want to start coding, so we will start soon. Okay, before we go on, I will need to. Okay, just a small reminder. Okay, a neural network is a predictor H that associates a label Y, which belongs to the set of all labels. Okay. Oh, sorry. This means nothing. A label means nothing. A label. Why? To any data X. Okay. And that is parameterized by theta, such that y equals h of x theta. Theta, remember, those are the weights and biases. You must be tired that I repeat that all the time, but I insist a lot on that because it's very important. Okay, now in this course, we will focus on finding theta. Okay, how do you get this optimal theta here such that you really get a predictor that is good at doing what you want, at associating your data to a label? Okay, and to start, I'm going to speak about an optimization technique that is called gradient descent. Okay. Sorry. Okay. So first, I will try to explain a little bit what is gradient descent in general. Then I will give you the algorithm. Okay. Gradient descent is an iterative algorithm designed to find the minimum of a function, which we call j of theta. The problem is usually stated as arg min of j of theta on theta. Okay. So this means finding the minimal value of theta that minimizes, sorry. It means that you want to find the value of theta such that j of theta is minimum. Okay. First, before going further, I would like to do a small reminder on what is the derivative of a function. Okay. The derivative of a function f noted f prime of x or df on dx is defined as f prime equals the limit when h goes towards 0 of f of x plus h minus f of x divided by h. Okay, so intuitively, this is physics intuition. It provides an approximation, a measure of the speed, the local speed on the curve trajectory and represents the slope on this point. So let me see what I mean. Here I represent a curve. Oh, not a very nice curve. This is a curve. Okay. Here what you will have is a large positive derivative. Okay. No, sorry. Negative derivative. Okay. Because if you look at f of x here, if you add a small h to x, you arrive around here. So f of x plus h is inferior to f of x. Okay. So if you compute this, you get something that is negative, and that is quite large because the difference between this and this is quite big. Okay. Now if you are here, okay, you get a small positive derivative. Because the difference between f of x plus h and f of x is smaller than here, but still it's positive. And if you are here exactly here, you'll get a null derivative. Okay. Okay. So back to our problem. Argmin of j of theta on theta can be solved by considering the equation dj divided by d of theta equals 0. Okay. Finding a minimum of the function, we know that on the minimum of the function, as here, basically, the derivative is null, is 0. The problem is, in practice, it's not easy to solve this equation. Why? Because in fact, sometimes this equation has no solution. Okay, there is no exact solution to this equation because the data we are dealing with is noisy. You know, remember I told you yesterday the data we are working on is stochastic when we do machine learning. Stochastic means that there is some noise, there is the random noise applied to it, and since you have random noise, sometimes the equation they just don't. Oh, sorry, excuse me. I'm really sorry. I have to take this call. Just a few seconds. Okay, I'm really sorry about that. Really sorry. Okay, so I was saying that yes, in practice, this kind of equation does not always have some solutions. Okay. But what we can do in practice is trying to find an approximation of the solution. So what we can do is to find an approximation of the solution. Okay. And gradient descent is an algorithm that iteratively converges towards the solution. Okay. How does it work in practice? Maybe what I can do is copy you an image which will be way better than what I can draw. No, that's not what I want to do. Okay, so let's go find this. It's in this. Just a sec. No, it's very, very, very ugly. Okay, so I'm sorry, I will need 1 more minute. Okay. Okay, this one is much better. Just need 1 more minute. Sorry. Okay, so this is an illustration of what gradient descent does. In practice, gradient descent, so GD for gradient descent, starts with an initialization of theta 0. So it's basically the first point of the algorithm. You see, it's an iterative algorithm. So you start from somewhere and then you iteratively refine your solution until it's satisfying to you. Okay, so here is your theta 0. I start from here. And then what you do, you make a step in the slope direction. Direction of the gradient. Okay. In fact, it's the opposite direction of the gradient. Okay. So what does it mean? If you are here, the gradient direction is there, all right? So if you want now to go in the opposite direction, you would go typically in this direction. So what you do is that you compute the gradient in theta 0, and then you use this gradient to go in the opposite direction. How you do that? You will compute theta 1 will take theta 0 minus some alpha derivative of j divided by theta on evaluated on theta 0. Okay, so this, it's exactly this. Okay, alpha is the size of the step. Okay, we call it a learning rate. I will come back to that later. And so we go from theta 0, we compute this gradient in theta 0, this arrow, and then we go in the opposite direction, and then we end up in theta 1, and we start again. Okay, and then you iterate until convergence. So what happens is then you are theta 1, so the gradient is like this, and then you go in the opposite direction, you end up at theta 2. But you see here, the gradient is smaller than here, so you do a smaller step, okay? And here is the same, a smaller step towards here, etc., etc. Okay. So in fact, iterate means you do theta I plus 1 takes theta I minus alpha dj over d theta evaluated on theta I. Okay. So this is the gradient descent algorithm. It's very simple. So something important, alpha is called the learning rate. A large alpha makes convergence faster, but there is a risk of missing the solution. Whereas a small alpha makes the convergence slower but safer. Let me explain that. First, I just realized that I've made a mistake in the previous here. I drawn a large negative derivative in this direction, which is a mistake. Okay, this basically, if this is my curve, my derivative here goes in this direction. I'm sorry. Okay. So what do I mean by large alpha makes convergence faster? Here you see with this alpha that was chosen for this, when I was here, I made a step here. If I had a larger alpha, my step would have been bigger. Maybe it would have gotten me here, or maybe here if it was really big, okay? And the problem is, if your step is too big, when you arrive around here, you will never reach the exact solution. You will basically go there, and then go there, and then go there, and then go there, because the step is too big to really stop there. So what happens is that your step is too big, you oscillate over the solution. And this can happen. This really happens a lot, in fact, in practice with gradient descent. And so that's what I mean by there is a risk of missing the solution. Conversely, if you choose a small alpha, when you arrive around here with the small alpha, you will be able to arrive here, no problem. But the problem is with the small alpha, when you are here, maybe you will end up here, and then here, and then here. And very quickly, very slowly, sorry, you will reach the end. Okay, so when you are here, you're happy because you can reach the solution. But when you are here, you are not happy because it's too slow. Okay, so this is the problem that you have to solve when you choose your learning rate. You want a learning rate that is quite fast. Okay, you reach the convergence, you reach the solution quite quickly, but at the same time, you want the solution to be precise. So you want a learning rate that is still quite little. Okay, there is another problem with gradient descent. There is a first problem, which is how do you choose alpha? And the second problem is convexity of the function. So gradient descent is guaranteed to converge towards the optimal solution if the function to minimize is convex. Basically, this is convex. If it is not, you can only converge to local minima. What does it mean? Let me draw another function. Okay, this is not convex. And now, if you start with theta 0 over here, you might end up with theta here, which is not your optimal solution. Now, if you start here, then you might end up here, but with a large learning rate, you might also end up here, which is your optimal solution. Okay, so in fact, when you have a function that is not convex, just like I'll draw here, the initialization is very important. Okay. It's crucial. And the thing is, in practice, in deep learning, the functions we minimize are not convex. Okay, so this is something that you should always be aware of. Okay, when we will train neural networks in deep learning, what we will really do is apply some kind of gradient descent to some kind of functions that look like this. So you have to know that the theta, the parameters that you will find when you will train your neural network, have a good chance to be non-optimal. Okay, and in fact, finding the optimal parameters sometimes is difficult. So it's okay. We know this is a known problem, so there's no big deal. It's just something that you have to be aware of. Do you have any question on that? No? No question? So if you have no questions, now is the time for me to speak to you about cost functions. Okay, and once you will have, you will know what is a cost function, you will have pretty much all the information you need to understand how we train your network. Okay. Sorry, bad window. Okay, let's speak about cost functions. So in this class, we consider supervised machine learning examples, which means we have a set of training data. Remember, I wrote it yesterday. I called it D equals a set of xi, yi. Okay, for y equals 1 to n, which are labeled, sorry, examples. We can use this training data to compute the performance of a predictor H as, so performance of H equals the sum of cost of yi h of xi over I equals 1 to n. Okay, this is very important. What happens is we have a set of labeled example. We know that for this X, for this data, the Y, the label is known. So we know that our predictor H for this X should predict something that is close to Y1. So this is predicted label. And this is the real label. And there is some kind of difference between them that we have to quantify. And this quantification is the cost function. Okay, what I call the cost function. We spoke a little bit of that yesterday when we spoke, remember, of how do you quantify the performance of certain machine learning tasks, such that the one we identified on YouTube, like the spam or not spam detection, or the genre detection or the genre classification of a video. Okay, so we spoke about confusion matrix, about false positive, false negative, etc., etc. This is kind of cost functions. Later, okay, I can also say that this performance. Now, if I say that H is in fact H of X theta, okay, I can write this performance of H as J of theta equals the sum over I equals 1 to n of the cost of the yi h xi theta. Okay. And here, I hope you understand that this J of theta is something that we want to minimize. Okay. We want this to be minimal. Why do we want J of theta to be minimal? We want our prediction, okay? We want our predictor H that depends on theta. We want our predictions of X on the learning sets to be as close as possible as the real labels. So we want the cost of this to be very small, sorry. And so minimizing this means that we want to find the theta that parameterize the predictor such that our prediction on the test set are almost perfect. And how do we do this? We do this using gradient descent. Okay, that's where we're going. But first, we have to define what are the cost functions, what are good cost functions, okay, for our problems. Okay. So the cost function could be any measure of dissimilarity between yi and h of xi. For example, if y belongs to 0, 1, which means we are doing binary classification, we can define a cost function C of A, B, which is 0 if A equals B and 1 if A is different of B. This is very natural to do this. So this is one possibility, but we could think of many other possibilities for the cost function. So how do we choose the proper cost function for our problem? Here I speak about binary classification, but it would be the same for multi-class classification or for regression, or we always need to find a cost function. In practice, this is where probabilities and statistics will help us. And this is where I won't really go into detail, okay? I just want to give you a general explanation of how we do it. In practice, we use cost functions that derive from a method called maximum likelihood estimation. So this is well known in probabilities. The idea is that we want to estimate, to estimate theta for which the probability of observing our training set is the highest. Okay. So this has a mathematical formulation that I won't get into detail. Okay. What is it's mostly statistics and is solved using a function called log likelihood. So it's just a parenthesis. I don't want to get into this kind of details. Maybe you know a little bit of this. I don't know how much probabilities and statistics you have studied before, but whenever you want to, this is related to a statistical problem called estimation. We want to estimate the parameters of a certain distribution, probability distribution. Okay, and usually what you do is that you sample points, you sample examples, and in our case the samples are the training set. Okay, and we want to say that the theta, so the parameters of the neural networks that we should choose are the one that maximize the probability of obtaining our samples, meaning of associating some labels to some data. Okay, and this maximum likelihood estimation, okay, that's the name of the method. To solve it, usually you go through a representation of the likelihood that is called the log likelihood, which has good properties for convergence. And what is really important in all I said is that usually there is a logarithm that appears here, and the logarithm you will find it in the two cost functions that it's the same cost function basically that I will introduce to you, which is called the cross entropy. So this cross entropy, you will find it probably when I will define it to you. You will find it a little bit odd. You will think, okay, why are we using that? Why not use a simple cost function? In fact, the log likelihood, the cross entropy, that I will explain you in a minute, has two good properties. First, it has a good property in the sense of this maximum likelihood estimation, and it has another good properties when we will look at the gradient descent, okay, because it has good gradients basically for convergence. So it might not be very intuitive to use cross entropy, but you'll see that in fact this is what works the best. Okay, so this is why the most. Oh, sorry. Usual cost function for classification is cross entropy. So I say most usual because in fact, you can always use other cost function if you want. There are some existing ones that may help you in some cases to get better results. It may happen. It's not always the case. And more importantly, it's never guaranteed. Okay. But cross entropy is usually the better choice. So you should always start with cross entropy, and later, if you have problems, maybe you can think of changing the cost function. Okay. In fact, there are two versions of cross entropy, so I will introduce you to both. The first version is for binary classification, and it's called binary cross entropy. Okay, and then you have a multi-class cross entropy. Okay. For binary classification, so we will call P equals P of Y equals 1, knowing X. Remember, this is what we said earlier. And 1 minus P equals P of Y equals 0, knowing X. Okay, and then let Q equals P of Y hat equals 1, knowing X. And 1 minus Q equals P of Y hat equals 0, knowing X. So Y here is the label, and Y hat here is output of the neural network. Okay, then we define the cross entropy, the binary cross entropy of y hat is equal to minus p log of q minus 1 minus p log of 1 minus q. Okay. Okay, this is the formulation of the cross entropy. And I hope you are thinking in your head that this is way too complicated. If you remember this, this that I defined earlier, this is way much simpler, okay? If the two labels are the same, you use 0, otherwise it's 1. Here, you have probabilities, you have logarithm, it's much more complicated. But in fact, it's complicated, but it has a meaning. So my goal is to show you what is the intuition between this cost function. So intuitively, cross entropy is a measure of dissimilarity between distributions. Distributions meaning probability distributions. Okay. So, for example, if p equals 1, okay, we have p and 1 minus p, which is a probability distribution, which is equal to run 0. Now, if we take Q equals 1, we have Q1 minus Q equals 1, 0. Okay. And the cross entropy of that, so binary cross entropy, I will call it BCE. Okay. BCE in that case is equal to 0. So that's perfect. We have a probability distribution of 1, 0. And this is the probability that our network is given, 1, 0. Then BCE equals 0. Perfect. Then what happens if we have Q equals 0.9? So meaning our network does not predict 1, it predicts 0.9. It's almost perfect, okay? Here, our probability distribution is 0.9, 0.1. And as you see, it's not very different from 1, 0. And in this case, BCE, binary cross entropy, is equal to 0.1. So it's very small. Now, if we take Q equals 0.5, we have Q1 minus Q equals 0.5, 0.5. It starts to be quite different, okay? Very different, even 0.5, 0.5 is very different from 1, 0, so it's not a good prediction, and in that case, BCE is equal to 0.7. And finally, if you get Q equals 0, you have Q1 minus Q equals 0, 1. So it's the worst prediction you can make. You are completely wrong, okay? The two distributions are opposite. Then the BCE is equal to infinity. Okay, in practice, it cannot really happen, but this means you are making an infinite mistake. Okay. So this is what cross entropy does. And remember that in practice, in our training data, we have P equals 0 or 1. Okay, this means that in practice, when we have a data that is labeled 1, we have this part of the equation that is equal to 1, so we have minus log of Q, and this is 0, so this part disappears. And when we have P equals 0, so if we have labeled, for example, our data that is not spam, then this is 0, and this is only log of 1 minus Q. So in fact, the equation gets simpler when you use it with the training data. Okay. Just a last comment on the multi-class cross entropy. Okay, so this is the binary cross entropy, and on multi-class classification. Okay. Remember, we have Pi, which is P of y equals I knowing x, and we call Qi the output of the softmax layer of the neural network. And so it's not called binary cross entropy anymore. It's just called categorical cross entropy, in Keras at least. This will be the sum on I equals 1 to n, the number of classes, of minus Pi log of Qi. So in fact, it seems simpler. It's not simpler because it's exactly this, except that you have more terms of the sum, okay? You have n terms, but it's exactly the same. Okay. So I won't get into much more detail. It's the same idea. And so now, finally, as I was saying earlier, in classification, we can, so, okay, this is a stop. In classification, we can write the performance of a predictor h of theta on the training set as j of theta equals the sum over I equals 1 to n, the number of examples in our training set, of the cross entropy of yi h xi theta. Our goal to get the best performance is to find theta such that j of theta is minimum. And we use gradient descent. Okay. Maybe we should have a break now, if that's all right. 10 minutes. What do you want? Well, what do you think is good?
I think
Yes.
10
10 minutes until 8 p.m.
yeah.
Is that all right?
Yes.
Okay. Okay. So let's have a small break, and then after that, I will show you some. I think I will stop with the theoretical class. Okay. I will show you some examples of runs of neural network, and then we can start the lab. Okay. See you in 10 minutes. Okay, I'm back. So we said a lot of things this morning again. I'm sorry, it's morning for me. It was morning for me. Now it's evening for you. I have to get used to that. Now, what I would like to do would be to try to be a little bit more concrete and show you examples of what it means to train your network. So I will start by showing you an image of the interface that I will use to illustrate some stuff on your network. So here is how the class now will go for the next 2 hours. It will be a time of the practical session. So the first practical lab, maybe I can already send you the topic. I'll do that right now. It's a little bit too early, but no problem. It's so first lab. It is there. Oh, sorry, it's still on my. Does everybody? I guess you all have a Google account, right? Can you raise your hand if you don't have a Google account? Because for the labs you will need a Google account. I'm downloading this. Okay, and now I can write you. So I guess that you all have a Google account. Have you ever used Google Colab? Because this is what we are going to use for these labs. Okay, I sent you an email. So in the lab we will use Google Colab. Okay, I'll write it in the chat. Google Colab allows you to run some deep learning code online on virtual machines that are located at Google's. And what is good with this virtual machine is that they have GPU. So it allows you to do maybe not deep learning, but at least advanced neural network learning. So it's quite nice. And what we will do in the first lab will be to try to get used to Keras. And to do this, we will try to reproduce the results I will be showing you right now. And the results I will be showing you in.
I think you forgot to share the screen of Google Colab.
No, I'm not showing it right now. Thank you, Billy. I want before going to the labs, I would like to oh, maybe in fact maybe I hope I didn't send you the. Oh, maybe I made a mistake. No, I didn't. Sorry. I will show you Google Colab just after that, but before I want to show you something else. And sorry, since I'm speaking, I can't. I'm having trouble doing two things at the same time. So I'm looking for an image to show you first. Probably around here, I guess. No, it's not here. Sorry. Visualization. Okay. Playground. Okay. Finally. Okay, I want to show you that first because this is how we can try to understand neural networks. So this is a screenshot from a platform called playground.tensorflow.org. Okay, and we will go to this platform in a minute. But before, I want to explain you a little bit what we will see on this platform. Okay, so playground.tensorflow.org. Okay, so you have here a neural network. You have the input layer. Sorry, input layer. And previously I have said We call this L0. Then you have hidden layers, L1 and L2 here. And here, this is your output layer, so F3. Okay, if you look at the problem is basically binary classification. You have blue points, you have orange points, and the real problem that you want to solve is now, here is a new point. Should that be classified as blue or should that be classified as orange? Okay, this is binary classification. So to solve the problem, you have a training set, and this is your training set, okay? And you are defining a neural network, and you can define several different neural networks using different number of hidden layers, different number of neurons for the hidden layers, but you see the output layer, you have no control on it. Why is that? Because since you are doing binary classification, you see here, the problem is classification, and I tell you it's binary because there are only two classes. Since it's binary classification, you don't have the choice of choosing the output layer activation function. It has to be a sigmoid activation function. Okay. For the output layer. Okay. But for the rest of the hidden layers, you have the choice to choose the hidden layer activation function. And in fact, you can choose here. Okay, here by default, it's a hyperbolic tangent, okay? But you can also get ReLU, linear, or sigmoid as well, right? You can choose whatever you want. Another thing that we just discussed here, learning rate. So this is related to gradient descent. It's the size, remember, it's the size of the step, the alpha here, the size of the step that we do when we go in the direction opposite to the gradient. So this is a parameter which we can play with. Now I won't comment the regularization because this will come tomorrow. Epoch here, you don't know the term, but it's related to the number of iteration of the gradient. So when you will do play here, you will see that the network is learning iteratively, and epoch kind of gives you a sense of that. And I think that's pretty much all I want to tell you right now. There are other things here, you see, ratio of training to test, okay, we don't really care about that right now. The noise equal to 0 is important. Yesterday, I told you that we work on stochastic data. So stochastic data means that the data that we have is not perfect. Here, when you look at that, you said the data is perfect. What we really want the network to get is to try to separate the blue from the orange. So we hope that the network will be able to tell you that inside here should be blue and outside should be orange. I think you agree. This is natural when we look at that. And this is very natural when we look at this data. But if you increase the noise, you will see that sometimes it's more complicated than that because you have some blue points inside the orange one and vice versa. Okay. So this is for the introduction. Now I will really show you the playground. Let me try to stop the sharing and to share. Okay, this. Can you see my screen now? Now you should see the playground, okay?
Yes.
So one thing you can do if you want is you can try to do it at the same time if you want to test it. So first thing I can show you now is the noise. Remember I said when we have stochastic data, we can have noise in the data, and you see an example of that. You see that sometimes the blue point here, they might be inside the orange point, and vice versa. The orange point might be inside the blue point. Okay, so this will make the problem more difficult. Right now, we don't care about making the problem difficult. We will keep the noise at 0. Okay. For now, what I would like to do is to have a very, very simple neural network with no hidden layers. So I have two input data, and one output. And this is exactly what we have discussed yesterday. I call that the perceptron. Remember? The perceptron is basically a single neuron. So here you have one neuron, and it connected to output, and that's all. Something I didn't comment either is this. These are the weights of the neural network. Remember the synaptic weights. So you see, I can try to train my neural network, and we will see what happens. So I train my neural network. So it's not evolving anymore, and we can't really see what happens. You see that here is kind of blue, here is kind of orange, and here there is some kind of degraded color. Okay, what we can do is discretize the output. Okay, you see that here there is a clear separation between one side of blue, one side of the orange. This is what the network is predicting. The network is predicting that on this side of the line here, you should have only blue points, and on this side you should have only orange points. So obviously the network is wrong. Do we agree on that? The network it's not a network, it's only a neuron. The neuron does not manage to make the prediction correct. Just a small comment. When you see this color, this light color, in fact, it's related to the probability. Remember, I said what we are predicting is a probability. Well, you can see here the probability. When you go on the left, you have a probability that is higher, closer to 1. And when you go on the right, it's closer to 0. In fact, here they say -1. Okay. Okay. So this means that basically a perceptron, a single neuron cannot really learn the complexity of this problem. But this I already told you somewhere in the class. When I spoke about the perceptron, I told you, okay, in class 2, maybe if you can find it. In class 2, I gave you at some point. Let's try to open it. If you have the PDF, when I explained the perceptron, I told you that sometimes that the equation of the separator can only be linear. I wrote something like this. And this is what happens here. The perceptron can only predict a linear function here, something that is a line basically, and the line is not complicated enough to really separate those two set of points. So we have to add some layers. Okay. So please help me. I need your help. What should I do? Should I add a lot of layers, or should I add only one layer but a lot of neurons? What do you think? Tell me. Or maybe you can vote. Who votes for adding more layers? No? You have no idea?
I think I vote option 2.
You would prefer one layer with more neuron, Billy?
More layer.
More layers. Okay. Okay, so let's start with more layers. How many layers? Maybe 3? Okay, let's try with 3 layers. Okay. It's not so bad. It's almost good, but doesn't learn. You can see that the shape of the separator is much more complex now. You see that it's not a line anymore. It's more complex. So it looks like the Nike logo, in fact, in that case. So this is also because of this hyperbolic tangent activation. Until now, we have only I have told you that we should always use ReLU. Okay. But let's not use ReLU in the first place. Let's try to use linear activation function, okay? If I use linear activation function, you will see something weird. Let me try again. Okay. You see what is going on here? When you use the linear activation function for the hidden layers, what happens is that you get a linear separator in the end. So this means that basically, even if you have built a large neural network here, what you really get is something that is exactly like one neuron, like the perceptron. So this is an important lesson. You should not use linear activation in the intermediate hidden layers because it doesn't help creating complicated neural networks. This is something I wanted to show. Now, if you want to use more to get more complicated neural networks, you should use hyperbolic tangent or sigmoid or ReLU. Okay. So remember, with hyperbolic tangent, we get something that is not bad but is not perfect. One detail that you can see right now, it's not exactly the same thing as earlier. Okay, earlier we had a shape that was located in another direction. Now it's looking down. Earlier it was looking up. Does anybody try to guess why this happens? Do you have any idea? Anyone? So Nam said overfitting. I didn't speak about overfitting right now, so I won't answer to that, but the answer is no. Nice try. We will speak about overfitting tomorrow, so right now, no overfitting. Now it's more simple than that. It's related to something we have seen together today. Remember, today I spoke about gradient descent and non-convex functions, and I told you, according to the initialization that you choose, you may not end up in the same local minimum. And this is exactly what happens here. When you look at this here, you are in a local minimum. It's not the perfect solution. It's one solution. And when you start again here, you see that all the weights here is 0.43, here is 0.11, etc., etc. Now, if I initialize again, my weights are different. It's minus 0.28, 0.32, etc. So basically, whenever I start again here, I reinitialize my network differently. I reinitialize my theta, my parameter, differently. And so I might end up in a different local minimum. Okay. So this is what happens, in fact. We go from a different initialization and we may reach a different solution. And this is important because this will always happen when you use deep learning. Okay, so I will just change the activation because hyperbolic tangent is nice, but as I said earlier, we should probably use ReLU. Okay. Let's try with ReLU. Okay, we still have the problem. So it seems that what we tried to add hidden layers did not really work well, or at least in this state, it's not enough. Either we could add even more layers. Let's try that. Okay, it doesn't work better, as you can see. Okay. Or what we can try to do is go back to the previous choice, okay, and add only one layer, but with more neuron. And if you do this, aha, this starts to look correct, okay? This is a good solution, a good possible solution. And as I was saying just before, you see that the solutions that we get here, if we start again, we may not end up in the same solution. You see the shape is different. Okay. Okay, very well. So we managed to solve this problem. Now, I want to show you something because it's important for what you will have to do in the lab. Okay. Suppose that instead of ReLU, you use a sigmoid function. Okay. So this is the sigmoid activation function. So remember, I told you on the output layer, activation function is already a sigmoid, but on the intermediate hidden layer, it can be a sigmoid, it can be something else. Let's use a sigmoid. What happens is, after some point, it's perfect, it gets a good result, so we're happy. Now, what happens if I do more layers? Okay, I will create 3 layers with 6 neurons each, and I will train my sigmoid, my neural network. And you see, it does not evolve. So when you have 1 layer with sigmoid, it works. When you have 3 layers, it doesn't work. And if I change sigmoid to ReLU, it works. Okay. So this is very weird. Okay. And this is due to a famous problem that we called vanishing gradients. I put it there. So tomorrow, vanishing gradients is a huge problem when you train neural network. And tomorrow I will explain you a little bit why this can happen and how can you prevent it. Okay. So this is the goal of tomorrow's class. But for today, in the lab, I will ask you to demonstrate what you just saw. So I do it again. You see that if you build a network with 3 hidden layers and 6 neurons for each layer, if I use a sigmoid activation function, I get nothing. And if I use a ReLU activation function, it works. Okay. So this is something I want you to recreate in the Keras lab. Now, maybe what I can do is show you a little bit about the collab file that I sent you. So can you see my, okay, yes, I can do that. This is what you should see. Okay, when you start the notebook I have sent you. So in order to see this, you should take the notebook I sent you by email and put it in your Google Drive. Okay, and then in Google Drive, you see when you click this, you have this open with Google Colab here. So if you don't have, sorry, I'm sorry, I'm not sharing. This is your Google Drive. I hope it looks like this. If you put the lab that I just gave you in your Google Drive and you double click it, it says here open with Google Colab. Okay, so for me it says that, but maybe for you it doesn't. If it doesn't, you can do something here. You can connect more apps. Okay, and when you click connect more apps, you can search for Colab. Okay, Google Colab or Collaboratory. Okay, maybe it's because I have it already. But if you do that, probably I think it's because I have it. Okay. When you do that and you open it like this, you will see exactly this part. Okay. So I will let you see what's inside this notebook. It's basically Python that you can execute by clicking here, for example. So this is only Python imports for the rest of the lab. The first function here is helps you generate data. Okay, so generate data exactly like I showed you on the playground, or at least it looks like the same. You see, this is the kind of data that you get. Okay, and this is something to plot the loss function. But today we won't speak much about that. So here is the first definition of a neural network. Okay, I am defining a neural network that has 2 layers, 1 hidden layer and 1 output layer. Okay, so let me show you what it looks like. You see that I ask you a first question right now. You can see that this network has 9 parameters, 6 parameters for the first layer and 3 parameters for the second layer. My first assignment is, can you explain why the neural network has 9 parameters? And so what did I build here? I build a network that takes 2 two input dimension, and a first layer which has two neurons with a ReLU activation, and then a second layer which is my output layer, which has a sigmoid activation and only one neuron. So in fact, I am building a neural network that looks exactly like this. An input dimension of 2, a first dense layer that has only 2 neurons, and a second dense layer that has 1 neuron, which is my output. And my activation for the hidden layer is ReLU. My activation for the last layer is sigmoid because I'm doing classification. So this is exactly equivalent, sorry, because I was not sharing, I'm really sorry, is exactly equivalent to this. Input dimension of 2, first layer of 2 neurons, and second layer of 1 neuron. Okay. And then once you have created this neural network, you can train it. Okay. So this is what you can see when you train a neural network. These are the optimization steps of the gradient descent that you can see, and you can see the evolution of the loss. The loss is basically my objective function J. Remember, the sum of the cost function over all the training steps, or over the training data. Okay, and you have the loss here, and you have the accuracy, which is the percentage of correctly classified points. So here my percentage is 62%. 62% is quite low, it's very bad. Okay. So you can see the evolution of the loss, okay, but it's not the loss. Remember, it's binary cross entropy. I have defined it here. I have defined my optimizer, which is gradient descent. In fact, it's stochastic gradient descent. I will explain you a little bit what it is tomorrow. With the learning rate, which I chose 0.03. And finally, here is the code, the line of code that allows you to train the neural network. It's model.fit. Model is the neural network. Fit is a function from Keras that allows you basically to fit this X with this Y. Okay. So this is basically the result. And now what I'm asking you to do for the rest of the seance is to basically do this. Okay. You have not enough material to do this, but you should have enough material to do this. Okay. So I want you to explain, to show me this exact phenomenon, the vanishing gradients that I showed you earlier. Okay, so the vanishing gradient, you can create a neural network of depth 5 with 4 neurons per hidden layer and a sigmoid activation function in the hidden layer. And you will observe that the network is not learning. And if you change the hidden activation function from sigmoid to ReLU, then you should observe that the network is learning. Okay, I'm stop talking. Now you can first try to load the lab into your Google Drive, trying to open Google Colab, trying to execute the lab to see that everything is working, and then you can try to think on the questions that I just asked. Okay, you have questions? Okay, so I leave you work on that. I'm here, obviously. If you have any questions, please ask. If you need to share your screen to show me that something is going wrong, please just do it. I'm here. In the meantime, I will send you what we wrote on class 3 until now. So maybe something I haven't told you. What I would like you to do, because in the end, eventually, I want you to give me back the results of the lab. Okay. So what you can do is create a notebook. You in the same notebook that everything is at the end after the assignment. You can copy paste parts of the code, and basically you can continue the notebooks with the answer to your assignment, and in the end you can return me the notebook. Okay. Which will be easier for me to correct. Is that clear? So the 4 assignments, please answer directly in the notebook, and so in the end, when you return me the lab, you can return me the notebook, and that's easier for me.
Yeah, we got it.
Okay, great, thanks. Is everything all right with everybody? Did you all manage to open Google Colab?
Yes, we can open the Google Colab and we are trying to do the first question.
Okay. Okay, great. Thank you. The others, can you just confirm quickly, either on the chat or vocally, that you managed to open the document?
Yes. Over
Okay.
Kundan.
Okay, thank you. What about the others? So I have a question from, from Longtan Nguyen, who asks, what is the purpose of input dim? So in fact, input dim, you try to change it, right? And it's still the same, and only the first layer needed actually. So that's true. Only the first layer needed actually, because this is the size, the dimension of the input of the network. So you see, we are working on points, on a cloud of points that are in 2 dimensions. Okay, you see that they are living on a plane basically. And so this means that the data that we have is of dimension 2. If you change it, I think at the fit, when you train the network, when you call the method fit, it should bug. It should not work. So if it works, I'm interested in looking at what you are doing. So for Vietnam, I have checked your code. It's perfect. Thank you. So the thing is, you could continue, but I don't exactly know what to do. The thing is, if you take too much advance, for me, it's okay if you if you go. I think for people who have already done deep learning, this first lab is really easy. So either I can quickly prepare you another topic if you want to try, but honestly, I think it's better if you consider that it's finished. And tomorrow I will try to have something a little bit more for you. So for me, it's okay if you disconnect. So Long Tan Nguyen is asking me how to submit the lab work. What you can do is you can send me a link because it's too early to submit the lab work anyway. You can send me a link towards your. You can share me basically your drive so that I can check, and that's all.